Welcome once again. In this session, I'm going to be having a live session, a live streaming of my study session. I'm going to be studying for a couple hours. So I'm going to be using the Pomodoro style whereby I have 25-minute study session and 5-minute breaks in between. I'll see how many hours I'm able to go. Basically, I'll be refreshing my knowledge on machine learning concepts. So a lot of machine learning related themes, a lot of topic related to machine learning and deep learning and generative AI. Those are the things I'm going to be studying in this session. So stay tuned. Sounds good. Alrighty. This is like a student learning new material by studying old exams that contain both questions and answer. Once the student has trained on enough old exams, the student is well prepared to take a new exam. Awesome example. So in supervised learning, you actually give the model correct examples and then use the test data as a way to test it out. Okay, regression model predicts a numeric value. That is why we say it deals with continuous variable. Alrighty. So these are the possible features that we can have. For example, if we want to calculate the future house price, the square footage, zip code, number of bedrooms and bathrooms, lot size, mortgage interest rate, property tax rate, construction cost, and number of homes, and then future ride time. So this is the Y in that case. We are predicting the price of the home. Okay. All right. So classification model predict the likelihood that something belongs to a category. So mostly like binary classification. Unlike regression models whose output is a number or continuous variable, classification model outputs a value that states whether or not something belongs to a particular category. So like for cancer, for example, they want to predict whether it's malignant or if it's benign. So that will fall under classification model. But if we want to predict the prices of goods and services or the prices of housing, because that's a continuous variable, you're using those features to be able to make the prediction. In that case, that is a regression model will be good for that. But for classification model, we are going to use stuffs like binary classification. Yeah, they are divided into two groups: binary classification or multi-class classification. Binary classification model outputs a value from a class that contains only two values. For example, a model that outputs either rain or no rain. Multi-class classification model outputs a value from a class that contains more than two values. A model that can output either rain, hail, snow, or sleet, that's multi-class. Alright, a regression will work on numbers. Binary classification will be working on is there rain or no rain. That's just two examples you're dealing with. Or multi-class, where you have is there rain, is it hail, is it snow or sleet. So check your understanding. If you wanted to use an ML model to predict energy usage for commercial buildings, what type of model will you use? Definitely we're going to use a regression model, because that is a type of continuous variable we are trying to check out for, which is a number. All right. Unsupervised learning models make prediction by being given data that does not contain any correct answers. Okay, then the unsupervised learning model, the goal of the model is to identify meaningful patterns among the data. In other words, the model has no hints on how to categorize each piece of data, but instead it must evolve its own rule. So it looks at the pattern and then it sees that, okay, this looks like all the blue parts, so it clusters it as cluster 1. It sees that all of these are the pink part, it clusters it as cluster 2. It sees that all these are the yellow part, it clusters it as cluster 3. That's it. A commonly used unsupervised learning is called clustering. The model finds data points that demarcate natural groupings. Clustering differ from classification because the categories aren't defined by you. So in classification model, you basically define the output you are expecting, you give it the result, but this is unsupervised because an unsupervised model might cluster a weather data set based on temperature, revealing segmentations that define the season. You might then attempt to name those clusters based on the understanding of the data set. So we see, for example, this blue part is the snow, the rain part is the yellow is the rain part, the slit is this red part, so it clusters them together, and then the fact that there's no rain is clustered there. Alright, what distinguishes a supervised approach from an unsupervised approach? Okay, an unsupervised approach knows how to label clusters of data. A supervised approach is giving data that contains the correct answer. This is correct. Yes, a supervised approach typically uses clustering. No, an unsupervised approach knows how to label clusters of data. I would say, okay, this is not true. Alright, so it's only this one that is true. An unsupervised approach doesn't know what the clusters of data mean based on your understanding of the data. It's up to you to define them. Interesting, I didn't know that. Okay, reinforcement learning model makes prediction by getting rewards or penalties based on actions performed within an environment. A reinforcement learning system generates a policy that defines the best strategy for getting the most rewards. So it's through reinforcement learning that they're able to train robots to perform tasks like walking around the room, and software programs like AlphaGo to play the game of Go. So let's check what that looks like. Oh, so this is AlphaGo that was trained by DeepMind. Alrighty, let's continue. Did it give me the opportunity to retry? Oh, it closes. Alright, let's try this again. So this is the correct answer. A supervised approach is giving data that contains the correct answer. The model's job is to find connections in the data that produce the correct answer. An unsupervised approach is giving data without the correct answer. Its job is to find groupings in the data. Okay. So generative AI is a class of models that create content from user input. So unlike the traditional ML models, with generative AI, you train the data, it has pre-trained data, and then it's able to create content from user input. For example, generative AI can create unique images, music composition, and jokes. It can summarize articles, explain how to perform a task, or edit a photo. Generative AI can take a variety of inputs and create a variety of outputs. Okay, like text, images, audio, and video. It can take and create combinations of these. For example, a model can take an image as input and create an image and text as output. Okay, so we can either have like text to text, where the text is an input and then it's returning back a text, like in ChatGPT, where it returns to us text format. And sometimes it can also have like DALL-E, for example, where it returns images, or video like Sora AI, whereby we are able to get video produced from the bot, from the GPT, or text to code, where ChatGPT is able to write code for us, and text to speech. So these are the different examples. So text to text, who invented the Le Mans race, and then it returns the text to us. Basically, it will return this based off of how it is trained. So if it is trained with the wrong data, the output will probably be wrong, but it can relearn and go from there. Text to image, so we can give it this, I want you to generate this image, and it does. Or text to video, or text to code, where it can print prime numbers. For number in numbers, its prime is true. For I in range 2, comma number, if number modulo I equals 0, its prime is false break. If it's prime, yeah. We can also kind of optimize this code by, instead of going all through to I, we can go to the square root of I, right? Because definitely anything from the square root of I upward is already being factored in, because there will definitely be multiples of numbers less than the square root of I. All right. Then also image to text, so you can give it an image and ask for what does this image look like. Alrighty, well, going quickly. So supervised learning tasks are defined and can be applied to a multitude of scenarios, like identifying spam or predicting precipitation, that is if it's gonna rain or not. Foundational supervised learning concept. Supervised machine learning is based on the following core concepts. We have data, the model, the training, the evaluation, and the inference. So data is the driving force of machine learning. Data comes in the form of words and numbers stored in tables, or as the values of pixels and waveforms captured in images and audio files. We store related data in datasets. For example, we might have a data set having images of cats, housing prices, or weather data. So datasets are made up of individual examples that contain features and label. So these are features. These are gonna be the independent variables, and then the label is what we want to predict. So if we have the date, the latitude, the longitude, to be able to know the location, the temperature, the humidity, the cloud coverage, and the wind direction, and the atmospheric pressure, we can use that to predict rainfall. All right, so the label is the answer, or the value we want the model to predict. In a weather model that predicts rainfall, the features could be longitude, latitude, temperature, humidity, cloud coverage, wind direction, and atmospheric pressure. So these are things that they use to predict whether it's gonna rain or not. Okay. Alrighty. So these are examples. So these are a data set is characterized by its size and diversity. As size indicates the number of examples, diversity indicates the range. These examples cover good data set are both large and highly diverse. The essence of the diversity is to be able to ensure we prevent bias in our data, where our data is actually tilted in a particular direction, which might not give us the best result. I think we still probably review bias variance trade-off. So for example, a data set might contain 100 years worth of data, but only for the month of July. Okay, using this data set to predict rainfall in January, we produce poor predictions, because this, even though it contains 100 years worth of data, it is only for the month of July in that particular location. So if we are using that to predict rainfall in a different month entirely, you'll probably be getting poor predictions. And even if you have some false negatives making you think that you're right, you will soon find out that that data is not the information you are deriving, or predictive modeling you are building from this data is not helpful. Conversely, a data set might cover only a few years but contain every month. This data set might produce poor prediction because it doesn't contain enough years to account for variability. So it says what attribute of a data set would be ideal to use in machine learning. We say large size and high diversity. Yes, a large number of examples that cover a variety of use cases is essential for machine learning system to understand the underlying patterns in the data. Alrighty, a data set can also be characterized by the number of its features. For example, some data set from whether the data set might contain hundreds of features. In supervised learning, a model is a complex collection of numbers that define the mathematical relationship from specific input feature patterns to cover output labels. The model discovers these patterns through training. So training, before a supervised model can make predictions, it must be trained. To train a model, we give the model a data set, which we call the training data, with labeled examples. The model's goal is to work out the best solution for predicting the labels from the features. We've discussed that the features are the independent variable which you're gonna use to be able to make proper calculation for your predictive modeling. Alright, so the model finds the best solution by comparing its predicted value to the label's actual value. So that check is how it tries to see if its prediction is optimal. So how many, so that is what we then use for our confusion matrix, which we discussed yesterday, to be able to know the true positive and the true negative, the false positive and the false negative, to be able to calculate that, okay, what percentage did it properly calculate correctly. And we discussed how to find accuracy yesterday, the precision and recall. All right, so based on the difference between the predicted and the actual value defined as the loss. So when we are talking about loss, we are talking of the difference between the predicted and the actual values. The model gradually updates its solution from that loss function. In other words, the model learns the mathematical relationship between the features and the label so that it can make the best prediction on unseen data, so that eventually when we bring a test data, that is a data set. So for example, we discussed yesterday that whenever we have like say for example 100 data points or 100% data, we'll break it down, say 70% is the training data and then the remaining 30% will be the test data. So we're gonna train the training data and then test it. After we've gotten a good predictive model, we then test it out with the test data to see how well it performs. So for example, if the model predicted 1.515 inches of rain, but the actual value was 0.75 inches, the model modifies its solution so that its prediction is closer to 0.75 inches. So it keeps updating it, and then after the model has looked at each example in the data set, in some cases multiple times, it arrives at a solution that makes the best predictions on average. Alrighty, so this is the label data, the model, and then it makes a prediction. Model compares its predicted value with the actual value and updates its solution, keeps updating there. The model repeats this process for each label example in the data set. So this is the data set. Move it to the labeled example. We have the model. It checks the prediction, compares it with the actual result, and then keeps updating. In this way, the model gradually learns the correct relationship between the features and the label. The gradual understanding is also why large and diverse data set produces a better model. Okay, large and diverse data set will produce a better model for us. Okay. During training, ML practitioners can make subtle adjustments to the configuration and features the model uses to make prediction. For example, certain features have more predictive power than others. Therefore, ML practitioners can select which features the model uses during training. For example, suppose a weather data set contains time of day as a feature. In this case, an ML practitioner can add or remove time of day during training to see whether the model makes better prediction with or without it. So after we've done that, we need to evaluate the model. So we evaluate a training model. Oh, my time is almost up. Alrighty. Want to take a break now and come back to discuss evaluation. Okay, let's finish this. I know time is up, but let's finish this. We evaluate a training. Yeah, we evaluate a training model to determine how well it learned. When we evaluate a model, we use a labeled data set, but we only give the model the dataset features. We then compare the model's prediction to the label's true values. Compare predicted values with, so it keeps making the comparison and then try to see, do I need to like retrain my data? So let's see, depending on the model's prediction, we might do more training and evaluating before deploying the model in a real world application. So let's check our understanding. Why does a model need to be trained before it can make prediction? A model needs to be trained so it won't require data to make a prediction. No. A model doesn't need to be trained. Models are available on most computers. No. A model needs to be trained to learn the mathematical relationship between the features and the label in the data set. This is the correct answer. Alright, once you're satisfied with the result from evaluating the model, we can use the model to make prediction called inferences. And then on label data, which is now like our test data, right? So in a weather app example, we will give the model the current weather condition like temperature, atmospheric pressure, and relative humidity, and it will predict the amount of rainfall we'll be expecting. Alright, let's test our understanding before we move on. So the following questions help you solidify your understanding of core machine learning concepts. Alright, so it says predictive power. Supervised ML models are trained using data sets with labeled examples. The model learns how to predict the label from the features. However, not every feature in a data set has predictive power. In some instances, only a few features act as predictors of the label. In dataset below, use price as the label and the remaining column as the features. So it says, which three features do you think are likely the greatest predictor of a car's price? So we have all of these features: color, miles, height, the gearbox, the make model, the length, the tire size, the wheelbase, the weight, and the year. To detect a price for a car, I would say that I need to consider for a fact the year the car was made, the make and the model of the car, and the number of miles on it. Those are very critical. So I'm going to go with this option. Yes. So a car's make and model, the year, and the miles are likely among the strongest. Even regardless of whatever the gearbox looks like, it doesn't matter. Or whatever the height is, it doesn't matter. But the year the car was made is critical. Alright, let's go to the second one. It says supervised and unsupervised learning. Based on the problem, you will use either a supervised or unsupervised approach. For example, if you know beforehand the value or category you want to predict, you will use supervised learning. However, if you wanted to learn if your dataset contains any segmentations or grouping of related example, you will use unsupervised learning, correct? Suppose you add a data set of users for an online shopping website and it contains the following columns. So we are saying we have last purchase amount, years in sign up, number of purchases, number of coupons used, education, marital status, and income. If you want to understand the type of users that will visit the site, would you use supervised or unsupervised? I will use unsupervised for this, and the reason why I'm thinking unsupervised is that unsupervised model is very good for you to be able to draw like segmentations or groupings, right? So I would choose unsupervised. Yes, it says because we want the model to cluster groups of related customers, we will use unsupervised learning. After the model clusters the users, will create our own names for each user. Say discount seekers, deal hunters, the surfers, the loyal, or the wanderers. Alrighty, let's test another one. It says suppose you add an energy usage data for homes with the following column: the square foot, the location, latitude and longitude, the year built, and kilowatts per hour per year. What type of machine learning model will you use to predict the kilowatt hours used per year for a newly constructed house? This would be a supervised learning because we are using all these features to be able to predict how much kilowatt hours will be used by this new user. Okay, suppose you had a flight data set with the following column: the departure airport, destination airport, date, time of day, the airline, the fuel price, and the coach ticket cost. If you wanted to predict the cost of a coach ticket, we want to predict the cost of a coach ticket, would you use regression? So because we want to predict a numeric value, I'm going to go with regression because we are doing a numeric value. Based on the data set, would you train a classification model to classify the cost? Based on the data set, could you train a classification model to classify the cost of a coach ticket as high, average, or low? Yes, but first need to convert the numeric values in the coach ticket cost to category values. That is correct. I'll do that. Yes. So it's possible to turn a numeric value into an ordinal kind of case where we put like a form of range saying that this is low, this is average, or this is high. So we are going to be converting those numeric values. We just kind of like say, for example, if it's greater than $500, it's on the high end. If it's between 100 to like $499, that is like average. If it's less than $100, that is low. All right, so we are in the last part, which is training and evaluation. I know I'm way past the 25 minutes, but I want to finish this question before we go. After we've trained a model, we evaluate it by using a data set with labeled examples and compare the model's predictive value to the label's actual value. Select the two best options. So after we've trained the model, we evaluate it by using the data set with labeled examples and compare the model's predictive value to the labels. Okay, if the model's prediction are far off, what might you do to make them better? Okay, we can retrain the model but use only the features we believe have the strongest predictive power. Okay, retrain the model using a larger or more diverse stuff. Correct, I'll do this as well. So I will either retrain the model by using only the features that I know have the strongest predictive power, just like when we're talking about how to predict car prices. You know, the year a car is made. For example, a car that was made in 2024 is definitely going to be more costly than a car that was made in year 2000. That's 24 years difference, right? And then we know that the make of the car also is a make and the model. For example, if you're dealing with like a Mercedes Benz, is different from you driving in a Toyota Corolla or a Nissan or Altima or something like that. Benz will always cost more, you know. So he says you are now ready to take to the next level. So he's telling us that we are ready to go to the next level to see that. So we are going to go to the crash course now as the next line of practice. That's where we're gonna come to. So we're gonna have a crash course. There are so many stuff on the crash course concepts that we're gonna go through. So we start with linear regression and keep going as much as we can cover, but more so because I know I did all of those yesterday. I also come to the large language models where we discuss that. So I might skip some and we do them later another time. Yeah. And then if time can permit, we do this production ML system. But we'll take a break now. I will be back in 5 minutes. So we'll take a break now. So we'll take a break now and I'll be back in 5 minutes. So we're going to have a deep dive into the linear regression model to get started. So we've done the prerequisites where we went through the introduction to machine learning. As a quick recap, we also discussed already about basically the different process of training a data, having a test data, and then we're gonna just quickly go now into one of the machine learning algorithm, which is linear regression. This is a statistical technique used to find the relationship between variables. So we definitely use the linear regression for a continuous variable. In an ML context, linear regression finds relationship between the features. The features are like the independent variable. It could be so many features which we use to predict our label. So when you hear of concept like feature selection, what that is just telling us about is we going through the different process of filtering our features or our independent variables to try to see which of these features will basically help me the most in my prediction. Sorry. All right. So for example, suppose we want to predict a car fuel efficiency in miles per gallon based on how heavy the car is. We know for a fact that when a car is very big, it consumes more fuel, but the smaller and compact the car is, the better the fuel efficiency. That's why when we are seeing something is 3.5 pounds in 1,000, that is a car that is like 3,500 in terms of weight, right? It consumes, it takes a lot of fuel, so 18 miles per gallon, but a 2.37, that's why you see like I think Nissan Sentra or Toyota Corolla, all of those compact cars, they have very good fuel efficiency. So we are plotting that to be able to see all of this. So we see the relationship where we have pounds in 1,000 here, and then we have our miles per gallon as our feature, as our label, and this is our feature, the pounds, the different pounds, such that when we now have a new test data, we can use it to predict for a fact the miles per gallon that is going to take. So if we have, for example, a new car that is, for example, 1 point something pounds, right, in 1,000, you should expect it to actually, have more miles per gallon, basically. So we can see this is a relationship. So we could actually create our own model by drawing a line of a best fit line. So they call it a line of best fit through the different point, such that when now we have one from this model that we have drawn through this line of best fit, we know that when the car is just about 1 pound in 1,000, it will take about 27 miles per 27 miles per gallon. So basically we are using this algebraic formula, y equals to mx plus b, where y is the miles per gallon, the value we want to predict, which is also called our label, and then the m in this case is the slope of the line, and then the x is the pounds, our input value. That is the independent variable, it keeps changing, and the b is our y-intercept. So sometimes it will be what we call the constant. Okay, in ML we write the equation for a linear regression model in this format: y prime, which is the predicted label, equals to b plus w1 x1, where b is our bias, the bias of the model. Bias is the same concept as the y-intercept in algebraic equation. Okay, in ML, bias is sometimes referred to as W0. Bias is a parameter of the model and is calculated during training. Okay, and then the W1 is the weight of the feature. That's the weight of our feature. It is the weight because you can see we are multiplying it by whatever our feature is. So the higher the W1, in this case, the higher the weight, which could actually tilt, because sometimes a huge weight could have an effect on your model in your prediction. That's what that weight is about. So weight is the same concept as the slope, m, in the algebraic equation. Weight is a parameter of the model and is calculated during training. And x1 is a feature, is the feature of the input. So during training, the model calculates the weight and the bias that produces the best model. Okay, so we are going to make the calculation of the bias and the weights. All right. In our example, we like to calculate the weight and the bias from the line we drew. So the bias is 30. So basically, the bias is 30, where the line the line intercepts the y-axis. So as we drew this line, let me see, it's 30. Yes, where it's met the y-axis. So this is it. This is the bias right here. So as we drew this line across, this is the bias right here. That is 30. While the weight is minus 3.6, the slope, and that's the slope of this line. Okay,
That's the slope of this line. I think it's calculated back from the distance. I've forgotten now. So the model will be y prime equals to 30 plus minus 3.6x1. Okay. So a model with multiple features, like, okay, for example, a model that predicts gas mileage could have additional features like engine displacement, acceleration, number of cylinders, horsepowers. B plus W1x1 plus W2x2 plus W3x3 up to W5x5. Remembering that W's are the weights, X is for the feature, and the Y prime is the value we want to predict. So these are the different calculations based on that. So we are seeing that by graphing some of the additional feature, we can see that there's also some linear relationship to the label miles per gallon. So we can see it's still kind of like a descending graph, right? A car's displacement in cubic centimeters and its miles per gallon rating. Okay. As a car's engine gets bigger, its miles per gallon rating generally decreases. Okay. This is also the relationship of the horsepower. So a car's horsepower and its miles per gallon rating. As a car's horsepower increases, the miles per gallon rating generally go up, because the higher the horsepower, meaning it's going to be consuming a lot of the fuel to be able to power it. A car's acceleration and its miles per gallon rating. As a car's acceleration takes longer, the longer it takes, the miles per gallon generally also increases. Alright, let's check our understanding. What parts of the linear regression equation are updated during training? We update the bias and the weights. Alright, so linear regression will go to talk of the next thing, which is the loss function. So the loss function, loss is a numeric number. Loss is a numeric metric that describes how wrong a model's predictions are. So, we said earlier in the first part where we discussed that it tells us the relationship, right? That, okay, this is the predicted value, this is the actual value, and this is the difference. That is what the loss is. Loss measures the distance between the model's prediction and the actual labels. The goal of training a model is to minimize the loss. So the purpose is we want to ensure that, because we could have drawn this line of best fit to be up here, we could have drawn it up here, but in that case we see that it's going to have a higher loss. So the line of best fit is the line that helps us to minimize the loss. So the goal of training a model is to minimize the loss, right? Reducing it to the lowest possible value. In the following image, you can visualize loss as arrows drawn from the data points. So these are the different data points. These are the different data points that we have in our data set. And this is the line of best fit from our model. These lines here is indicating our loss. So the arrows show how far the model's prediction are from the actual value. So you want a model whereby the total losses are smallest, right? So in statistics and machine learning, loss measures the difference between the predicted and the actual values. Loss focuses on the distance between the values, not the direction. For example, if a model predicts 2, but the actual value is 5, we don't care if it is -2 or -3 or +3. Instead, we care about the direction, the distance, and the distance in this case is gonna be 3. Okay, thus all method, that is why whether it is downward or upward, it doesn't matter. It's just what is the distance for the loss. All right, so all methods for calculating loss remove the sign. The two most common methods to remove the sign are: you take the absolute value of the difference between the actual value and the prediction, hence what we call the mean absolute value. So the mean absolute value, which we're talking about, helps us with calculating the loss, in that with the mean absolute value, you are looking at the distance. And since, if for example you don't want to care about whether something is negative or positive, you have to use absolute value, because the absolute value of +1 is 1, the absolute value of -1 is still 1. So that is why one of the way we remove that sign is using the mean absolute error, which is the average of L1 losses across a set of examples. So we are doing 1/n in terms of mean. That mean is also the synonymous to average of the summation of the absolute value, which is actual value minus the predicted value. Okay, then another way you can also remove the negative of something is by using the square of that thing, right? So when you do the square of that thing, it removes the plus, because the square of -2 is 4 and the square of 2 is also 4, right? That also does the same thing. So that's why I say square the difference between the actual value and the prediction, or taking the absolute value of the difference between the actual value and the prediction. So types of loss. In linear regression, there are 4 main types of loss, which are outlined below. So we have the L1 loss, which is the sum of the absolute values of the difference between the predicted values and the actual values. So remember, the loss is actually the difference between the actual value and the predicted value. So actual value minus predicted value gives us the loss. If we do the absolute value of that helps us. And then the L1 loss will be the summation of the absolute value of that. So basically, if we are doing of all these different points, let's say this is 2, let's say this is 1, let's say this is 1.5, let's say this is 0.5, summing all of those losses will be able to help us to calculate the L1 loss. The mean absolute error, that is the average of L1 losses across a set of examples. So 1/n to find the average across that. The L2 loss is the sum of the square difference between the predicted values and the actual value. So we have the summation of the actual value minus the predicted value, and just square that. The mean squared error is the average of L2. So the L2 loss is the sum of the squared difference. So L1 loss is the sum of the absolute. So L1 is dealing with the absolute value now, and then the L2 loss is dealing with the squared difference between the predicted and the actual value. So when we do the square difference of the actual value minus the predicted value and squared it, the summation is the L2 loss. Whereas the mean squared error, once you see mean, we recall average. So that's why we are doing 1/n of that same summation of the squared of the actual value minus the predicted value. So the functional difference between L1 loss and L2 loss, or between MAE, which is mean absolute error, and the mean squared error, is actually squaring. When the difference between the prediction and the label is large, squaring makes the loss even larger. So when we see that the difference is already large, we don't want to square in that case, because then it just takes it off the chart. So when the difference is small, less than 1, squaring makes the loss even smaller. So when processing multiple examples at once, we recommend averaging the losses across all the examples, whether using MAE or MSE. That's why we not just go and just square it and do the sum and go forward with the L1 loss or the L2 loss, but preferably to go through the process of using the mean absolute error or the mean squared error. Alright, so how do we calculate the line of best? So using the previous best line fit, we will calculate L2 loss for a single example. So how do we do that? We have the weight, we have the bias. So if the model predicts that a 2,370 pound car gets 21.5 miles per gallon, but it actually gets 24 miles per gallon, we will calculate the L2 loss. To be able to calculate the L2 loss in this case, right? So we go so we already have 21.5 miles per gallon. How do we do that? We recall that for our prediction is to calculate y, or y prime is equal to our bias plus weight times feature value. So in that case, what is our bias? 30. So 30 is here, plus what is our weight? Minus 3.6. Minus 3.6 times the 2.37. Why is it 2.37? Because we were saying that we were doing it 1,000 pound per gallon. So if it is 1,000 pound per gallon in this case, right? So we have to divide any number in its thousands by 1,000. That is why we are using 2.37. So that gives us 21.5. However, when it was modeled, we were told that we got the label to be 24. So and we are told now to calculate L2 loss. L2 loss is the summation, but in this case, since we just have one, we just go straight to the actual value minus the predicted value and squared it. What is the actual value? 21.5. What is the 24? The what is the prediction? So prediction minus actual value. Either way, it doesn't matter. Whether actual value minus prediction, since we are squaring, it doesn't matter. So we can say the prediction that we got, which is our solution, is 21.5. So 21.5 minus 24. Why 24? That's our label or the actual value, and then squared it. So that gives us 6.25. So how do we choose a loss? That's a critical question, because since you know that we could actually either do the mean absolute value, mean absolute error, or the mean squared error. So how do we choose the loss, right? It says deciding whether to use MAE or MSE can depend on the data set and the way you want to undo certain predictions, okay? Most feature values in a data set typically fall within a distinct range. For example, cars are normally between 2,000 and 5,000 pounds and get between 8 to 50 miles per gallon. An 8,000 pound car or a car that gets 100 miles per gallon is outside the typical range. It is called an outlier. That is not the normal range of car. That is an exception. That is why it is called an outlier. So an outlier can refer to how far off a model's predictions are from the real value. For example, a 3,000 pound car or a car that gets 40 miles per gallon are within the typical range. However, a 3,000 pound car that gets 40 miles per gallon will be an outlier in terms of model's prediction, because the model will predict that a 3,000 pound car will get between 18 and 20 miles per gallon. What does that mean? Normally, a 3,000 pound car will have an average 18 and 20 miles per gallon. However, there are exceptions whereby maybe the engine of this car is built uniquely, hence it's having a larger miles per gallon than average. So when choosing the best loss function, consider how you want the model to treat outliers. Very critical. For instance, the MSE moves the model more toward the outlier when we do the mean squared error, because you are squaring the something, so it increases the typical range, right? So it moves it towards the outlier. while the MAE doesn't. L2 loss incurs a much higher penalty for an outlier than L1 loss. L1 loss is for the mean average, right? For example, the following images show a model trained using MAE and a model trained using MSE. The red line represents a fully trained model. So this is a fully trained model, right? That will be used to make prediction. The outliers are closer to the model trained with MSE than to the model trained with MAE. So this is the outliers now. You see, it brought it a little bit closer to it because it's trained with MSE. This is MAE. A model trained with MSE moves closer to the outliers, while a model that is trained with MAE is farther from the outlier. Alright. So MSE, know the relationship between the model and the data. So MSE, the model is closer to the outlier but farther away from most of the other data points with MSE. While MAE, the model is further away from the outlier but closer to most of the data points. So we are seeing these two plots. So one of them, everything stays in between. Okay, so it says which of these two data points shown in the preceding plot has the higher mean squared error? So what are the outliers in this case? So it says the model is closer to the outlier but farther away from most of the data points in MSE. But MAE, the model is farther away from the outlier. So this is MAE because it's farther from the outlier, but you see most of the data points were well covered. But here it's kind of closer to the outlier. So I would choose the one on the left. Oh, it says I'm wrong. The 6 examples on the line incurs a total loss of 0. The 4 examples not on the line, oh, so I have to actually calculate it and see the distance. So not just by looking, that makes sense. So I have to calculate the distance of each. That's what it's telling me to do, because that's how we got to that solution. So it looks at this and then calculates the distance here, because when you choose here, so when you choose here, the 8 examples on the line incurs a total loss because all of these are on the line. Okay, however, although only 2 points lay off the line, both of these 2 points are twice as far off the line as the outlier points in the left figure. So they are more farther away, but these ones are closer. Okay, it's farther away from most of the other data points, so this is farther away. Okay, but which one is the outlier? Because it keeps all of these as 0 0 0 0, but when it gets here is 2. This is 2 points away, and then it's 2 squared, that is 0.8. But even these are 1 point away, 1 point away, 1 point away, 1 point away, and because they are 1 point away in their distances, it is 1 square, 1 square, 1 square, 1 square, 1 square. So okay, so when we check the loss of each of these, so this loss, that is the distance between here, the distance between here, the distance between here, the distance between here, right? I wish I could actually draw on it. So you say the 6 examples on the line incurs a total loss of 0. So that is fine. There's no because they are all on the line is 0. but the, for example, not on the line are not very far off of the line. So even squaring their offset still yields a low value. The MS is 0.4. So this is why this one is right, because when we check the distance, this is 2. This is 2. And 2 square is 4. 2 square is 4. Divide by 10, that is 0.8. Because 4 plus 4 is 8. 8 divided by 10 is 0.8. But this, even though there are 4 different points, 1 square, 1 square, 1 square, 1 square, that is 1111, which is 0 over 10 is 0.4. That makes sense. Okay, we are at gradient descent. So we have to pause here and refresh this. So we're gonna take another 5 minutes break and be back afterward to continue. So we'll take a 5 minutes break and then continue. I want to start the timer. All right, we'll be back shortly. All right, we'll get started.
We'll get started on the next session where we'll go to discuss gradient descent.
So gradient descent is a mathematical technique that iteratively finds the weight and the bias that produces the model with the lowest loss.
So since we knew that one thing that is critical for us to be able to build a very good model is to have a small loss, right? So the gradient descent is that technique that iteratively finds the weight and the bias that produces the model with the lowest loss. So gradient descent finds the best weight and bias by repeating the following process for a number of user-defined iterations. The model begins training with randomized weights and biases near zero, and then repeats the following process. So calculates the loss with the current weight and bias, determine the direction to move the weight and the bias that reduces loss, move the bias and the weight values a small amount in the direction that reduces loss. Return to step 1 and repeat the process until the model can't reduce the loss any further. So basically the diagram below outlines the iterative steps gradient descent performs to find the weight and the bias that produces the model with the lowest loss. So it has weight and bias, takes it into the model, and then from that makes prediction. It determines the loss, right? But then we know that how does this model come about? It has data sets. This is the this part tells us the data set that we are using to train the model we are working on, right? This tells us the label, what we are trying to predict. Okay, so it goes on the prediction. We know that we need, why we are moving from this label to the prediction to get a loss is that the loss is calculated as the distance between the actual value of our label and the prediction. So we've done that prior where we calculated the loss by saying loss is actually actual value minus the prediction, the summation of the actual value. So if we are dealing with the L1 loss, we are dealing with the summation of the mean of the average, of the absolute value, of the absolute value, the average of the absolute value, the summation of the absolute value. However, if it is a squared error, we are a squared L2 loss, we are dealing with the summation of the squared error, okay, or the squared loss. Makes sense. All right, so basically that's how we calculate the loss. So we determine the loss. We know the loss now. It determines the direction to move the weight and the bias. Do I want to move it upward? Do I want to come a little bit down? Whatever the direction, so it moves a small direction in the a small amount in the direction to reduce loss. It repeats the process, goes again, and we iteratively go on to calculate that. So if you want to see the math behind gradient descent, it says we should click the plus. So in this case, this is it. Just like we're saying, the model start training by settling from 0 0. All right, calculate the mean square error, which is going from each of these miles per gallon. Is going to subtract them, minus 0 on all of them, squared it, so the loss at this point, and divide it because we are doing the average of the mean. So this is mean squared error loss, right? You get 303. So you calculate the slope of the tangent to the loss function. So the weight slope is negative 119.5
3.7 and the bias slope is negative 3.4. So how do we calculate slope? So remember, this is like getting very mathematical, but basically we write this equation. F of x is w times x plus b. B is the bias, w is the weight, right? So we'll write the actual values as y, and then use that to be able to say we'll calculate the mean squared error using 1 over m summation from all the values I equals to 1 to m, and then go subtracting it from the actual values, right? And then they do some differentiation. This is getting into like calculus and all of that. So I will skip the math. But it's a lot to be able to do that. So let's skip the math because of our time. So, but basically, from the loss now, we now move a small amount in the direction of the negative. So we keep moving, changing the iterating, moving, changing the bias, and see how we keep reducing the loss. There will come a point in time as we keep updating the weight and the bias that there is no significant change in the loss. When we come to that point, it's what we call it has converged. It's the point of convergence. So from this point of convergence, we are good to go with that weight and bias at that time. So you can see that the loss gets lower with each updated weight and bias. In this example, we stopped after 6 iterations. In practice, a model trains until it converges. When a model converges, additional iterations don't reduce the loss more. So when it has reached that convergence point, you are seeing just maybe 3 place or 2 place or 4 place decimal point changes. So there's no really a significant change happening. To confirm the model has converged, you want to continue training until the loss has stabilized, where you are getting something like maybe 35.56, 35.54, 35.53, that kind of thing. You know that it has reached a point of convergence. All right, so model convergence and loss curve. So this is it. So when training a model, you will often look at the loss curve to determine if the model has converged. The loss curve shows how the loss changes. So we see it's coming from here where it was so big and major changes, and then at a point it reached this point where there is really no significant change taking place. All right. So we see, you can see that the loss dramatically decreases during the first few iterations, then it gradually decreases before flattening out around the 1000th iteration mark. After the 1000th iteration mark, we can be mostly certain that the model has converged. Alright, so this is what it looks like. It reached that convergence point, and at that point you are good to go. Alright, so at around the 400th iteration, we can see the gradient descent has found the weight and the bias that produce a better result right here. Okay. Alright, so what's the role of gradient descent in linear regression? Gradient descent helps to determine what type of loss to use when training a model. Gradient descent remove outliers from the data set to help the model make better prediction. Gradient descent is an iterative process that finds the best weight and bias. I'll choose this. Yes. So convergence and convex function. So the loss functions for linear models always produce a convex surface. As a result of this property, when a linear regression model converges, we know the model has found the weight and the bias that produces the lowest loss. Alright. So these are the points, the convex surface, this is the point of convergence, right? So we see it here. that is losing the distance in the convex shape. Alrighty. So loss graph showing gradient descent points at its lowest point. So these are the different lowest points. So in linear regression, model converges when it's found the minimum loss. Therefore, additional iterations only cause gradient descent to move the weight and the bias values in very small amount around the minimum. If we graph the weight and the bias points during the gradient descent, the point will look like a ball rolling down a hill, finally stopping at the point where there's no more downward slope. That's what we see here. So it's like a ball is rolling down the hill, and then it's able to get to this point where it's fine. There's no more downward slope. Notice that the black ball point creates the exact shape of the loss curve, a steep decline before gradually sloping down until they've reached the lowest point on the loss surface. It's important to know that the model almost never finds the exact minimum for each weight and bias, but finds a value very close to it. It's also important to note that the minimum for the weight and the bias don't correspond to zero loss, only a value that produces the lowest loss for the parameter. Alright, that's good. Alright, the next thing is what we call hyperparameters, where we deal with like learning rates. So hyperparameters are variables that control different aspects of training. Three common hyperparameters are learning rates, batch size, and epochs. In contrast, parameters are like variables. Parameters are the variables like the weights and the bias. They are part of the model itself. In other words, hyperparameters are values that you control. Parameters are values that the model calculates during training. So when we are talking of hyperparameters, they control different aspects of the training, and they help us, there are values that we can control. So what is there? We have three majorly: the learning rate, the batch size, and the epochs. So what is the learning rate? The learning rate is a floating point number you set that influences how quickly the model converges. So this is a floating point number that we set that indicates how quickly our model will converge. If the learning rate is too low, the model will take a long time to converge. However, if the learning rate is too high, the model never converges because it's going to just run through, but instead bounces around the weight. So if the learning rate is too high, it's just going to bounce. It's just going to be bouncing. It's not going to be able to experience that reaching of the minimum point through going through the gradient descent. The learning rate determines the magnitude of the changes to make to the weight and bias during each step of the gradient descent process. The model multiplies the gradient by the learning rate to determine the model's parameters, weight and bias values for the next iteration. So in the third step of gradient descent, the small amount to move in the direction of negative slope refers to the learning rate. So when we're talking about gradient descent, when we say that it moves in either direction in a small amount, that is the learning rate. So the difference between the old model parameter and the new model parameter is proportional to the slope of the loss function. So a learning rate that is too large never converges because each iteration either causes the loss to bounce around or continually increase. Alright. So the ideal learning rate is problem dependent. Yeah, you cannot just say 0.01. It depends on the problem. Batch size is a hyperparameter that refers to the number of examples the model processes before updating its weight and bias. So batch size is a hyperparameter that refers to the number of examples the model processes before updating its weight and bias. You might think that the model should calculate the loss for every example in the data set before updating the weight and bias. However, when a data set contains hundreds of thousands or even millions of examples, using the full batch isn't practical. So basically, this is the number of examples the model processes before updating its weight and its bias. That makes sense. Two common techniques to get the right gradient on average without needing to look at every example in the data set before updating its weight and bias is stochastic gradient descent and mini batch stochastic gradient descent. So stochastic gradient descent uses a single example, a batch size of 1 per iteration. Given enough iterations, stochastic gradient descent works, but it's very noisy. Noise refers to variations between the training that can cause the loss to increase rather than decrease during an iteration. Stochastic is random, yeah. So stochastic indicates that the one example comprising each batch is chosen at random. Model trained with stochastic gradient descent showing noise in the loss curve, okay? These are epochs, that's the time. So mini batch stochastic gradient descent is a compromise between full batch and stochastic gradient descent. For n number of data points, the batch size can be any number greater than 1 and less than n. The model chooses the examples included in each batch at random, averages their gradient, and then updates the weight and bias once per iteration. Okay. When training a model, you might think that noise is an undesirable characteristic that should be eliminated. However, a certain amount of noise could be a good thing. In later models, we will learn how noise can help a model generalize better and find the optimal weight and bias in a neural network. Neural network is the bedrock of deep learning, is the bedrock of generative AI. So epochs during training, an epoch means that the model has processed every example in the training set once. For example, given a training set with 1000 examples and a mini batch size of 100 examples, it will take the model 10 iterations to complete one epoch. So training typically requires many epochs. That is why you see that the cost of training a ML model is very costly. It's very, very costly. The number of epochs is a hyperparameter you set before the model begins training. In many cases, you will need to experiment with how many epochs it takes for the model to converge. Alright. So it says, what's the batch size when using a mini batch stochastic gradient descent? Let's check. So this is batch type when weight and bias different occur. So we say for full batch, after the model looks at all the examples in the dataset, for instance, if a dataset contains 1000 examples and the model trains for 20 epochs, the model updates the weight and bias 20 times once per epoch. For stochastic gradient descent, after the model looks at a single example from the dataset, for instance, if the dataset contains 1000 examples and trains for 20 epochs, the model updates the weight and bias 20,000 times. Why? Because it says for stochastic gradient descent, after the model looks at a single example from the data set, it updates the weight and the bias, so 1000 times 20. While for mini batch stochastic gradient descent, after the model looks at the example in each batch, for example, if a data set contains 1000 examples and the batch size is 100 and the model trains for 20 epochs, the model updates the weight and bias 200 times. How did we come to that number? It says it updates the weight and the bias after the model looks at the examples in each batch. So if it's having 1000 and it has a batch size of 100, so how did we now come to the 200? When weight and bias updates occur, it says after the model looks at the examples in each batch. Okay, when it looks at the example in each batch, for example, if the data set contains 1000 examples, so we have 1000 examples and it's taking a batch size of 100, so the model is training. Oh, okay, so each time it goes is like 10 times, but since it's 20 epochs, it's 200, so times 2. Okay, so it says during training, an epoch means the model has processed every example in the training set once. For example, giving a training set with 1000 examples and a mini batch size of 100 examples, it will take 10 iterations for one epoch. So if it now says if it takes 10 iterations for one epoch, right, 1000 divided by 100 takes 10 iterations to complete one epoch, then it's doing 20 epochs. That is 10 times 100. Okay, so what is the best batch size? I would say it depends. Yeah, it depends on the data set and the available compute resources. Which of the following statements is true? Larger batches are unsuitable with many outliers. Doubling the learning rates. So let's go to the learning rate. So if we double the learning rate, the learning rate determines if the learning rate is too low, the model can take longer to converge. However, if the learning rate is too high, the model never converges, but instead bounces around the weight if it's too low. So in the question I'm asked, it says which of this is true? Doubling the learning rate can slow down training. No. If we double the learning rate, what it's doing is that it accelerates it, right? Because it says if the learning rate is too low, the model can take long to converge. However, if the learning rate is too high, it never converges, but instead bounces around. The goal is to pick a learning rate that is not too low or too high so that it converges quickly. The learning rate determines the magnitude of the changes to make to the weight and bias during each step of the gradient descent. Okay. Yeah. So I think the first one, larger batches are unsuitable. For that, I will choose this. No, by averaging more gradient descent, larger batches can help reduce the negative effect. Okay. So this is it. Doubling the learning rate can result in a learning rate that is too large. Oh, it becomes too large, and because of that, it can cause the weight to bounce around. Okay, that's the meaning when you say doubling. So we are increasing it and it becomes too large. That makes sense. All right. Using Keras. Let's just test our knowledge because of my time. Before we go to... All right. Which of the following is an example of a parameter that is calculated during training for a linear regression? Is part of a parameter that is calculated. We have learning rates and hyperparameter. The prediction, the label is the feature we have. It's a parameter that is calculated. I will choose weight. All right, fill in the gap. Suppose you're building a linear regression model to predict the sale price of a used car. The training data set includes the following information: sale price, model year, MSPR, odometer reading, gas mileage. How many weights will there be for this model? So we're going to have 1, 2, 3, 4. I will say 4. Review the graph below. What is the mean squared error? So the mean squared error is the summation, right? So this is, all these are 0. So 1, 2, 3, 4, 5, 6, 7, 8. So this is 2. The distance here is 2. So this is 2. This is 2. 2 square is 4. 2 square is 4. 4 plus 4 is 8. So 8 over 10, that's 0.8. Which of these controls the size of the steps? The size of the steps of the gradient descent algorithm. I will say learning rates. Suppose you are training a linear regression model, and after about 100 iterations, you notice that the loss is high and trending downward, but not by significant amount. What is likely the problem? So suppose you are training a linear regression, and after about 100 iterations, you notice that the loss is high and trending downward. See, your data set does not have enough examples. No. Your data set has too many examples. No. Your learning rate is too large. That'll be my guess. that is too large, because now, because it's too large, it's surpassing that. So let's see. I'll probably get some. Okay. All right. So it says that if the learning rate were too large, I will expect to change. So it's not giving me the option. So we got 4. I got the learning rate 0.8. I got 4 here. I got correct. Said we passed. So do I want to test it again? Let me test it again. If I'll get it again. So let's see which of this is a parameter. So we said weight. Fill in the gap. We said 4. We chose this 0.8. This is learning rate. So this is too small. Yeah, that's what I mean. So if the learning rate is too low, loss values will decrease very slowly. So learning new things, right? So we just did the test. We just finished the test on linear regression. I know that time fails me now. I would have gone to the actually building the algorithm itself and trying that out. But we'll go forward. Next, we'll be considering logistic regression, which is very, very interesting. That will be the next line of action. So we'll take a break here and we'll be back. So we'll take a break. Let me turn on the timer for another 5 minutes break. We just completed a huge session. This is interesting. So we are going to continue with logistic regression shortly. So we take a break, a 5 minutes break. we get started with logistic regression. All right. For logistic regression, this is going to take us all right, we continue. Identify use cases for, so the learning objectives for this case is we identify use cases for performing logistic regression, explain how logistic regression models use the sigmoid function to calculate probability, compare linear regression and logistic regression, explain why logistic regression uses log laws instead of a squared laws, and explain the importance of regularization when training logistic regression model. Those are things we will cover in this concept. Alright. In the linear regression model, we explored how to construct a model to make continuous numerical predictions, such as fuel efficiency of a car. But what if you want to build a model to answer questions like, will it rain today? That is a yes or no question. Is it email, spam or not? Or is this cancer cell malignant or benign? Or will this customer purchase or not? So it's yes or no question or something like that. The model introduces a new type of regression called logistic regression that is designed to predict the probability of a given outcome. Alright. So in logistic regression, we actually use a sigmoid function, so calculating a probability with a sigmoid function. Many problems require a probability estimate as output. Logistic regression is an extremely efficient mechanism for calculating probabilities. Practically speaking, you can use the return probability in either of the following two ways. So there are two ways we can use it. Applied as is. For example, if a spam prediction model takes an email as input and outputs a value of 0.932, this simply says that it is 93.2% spam. Okay? Or we can convert it to a binary category of true or false, spam or not spam. This module focuses on using the logistic regression model output as is. In the classification module, we'll learn how to convert the logistic regression model into a binary category. So to be able to deal with that, we use the sigmoid function. You might be wondering how a logistic regression model can ensure its output represent a probability, always outputting a value between 0 and 1. As it happens, there is a family of functions called logistic functions whose output has those same characteristics. The standard logistics function, also known as sigmoid function. Sigmoid means S-shape. Okay. Has the formula f of x is 1 over 1 plus exponential negative x. So we see the way the sigmoid function works is that we see that most of the values are going to be between 0 and 1. It turns any number you produce, any number you give it turns them to either a value of 0 or 1, and we can test it out. Whatever number you put as x in this function, it will either give you a value within the range of 0 and 1. So that's how sigma functions work. So as the input x, increases, the output of the sigma function approaches but never reaches 1. So it's gonna be very close to 1, 0.9 something, and similarly, as the input decreases, the sigmoid function output approaches but never reaches 0. So that's how it works. So we could take a deep dive into sigmoid function to see how it works, but because of our time, we won't do that. Because of it will take some time to check out the math. But basically, it's just understanding that sigmoid function is going to transform our function, whatever input variable we give it, to something within the range of 0 and 1. Transforming linear output using the sigmoid function. So the following equation represent a linear component of the logistic regression. So we have z equals b plus w1 x1 plus w2 x2, where b is the bias, w is the representation of the weights, and x are the feature variables. To obtain the logistic regression prediction, the z value is then passed into the sigmoid function. So after we've calculated the z value from all of this, we input it into our sigmoid function to be able to know what we are getting. If it's something close to 0, then it's probably going to be indicating false. If it's probably 1 or close to 1, because it cannot be 1, it will generate maybe true. So we see if we have this z equals to 2x plus 5, after calculating, we'll get a particular value, and then whatever value we get, we input it into the sigmoid function. Alright, so let's check our understanding. So let's check in this figure. It says a linear equation becomes input to the sigmoid function, which bends the straight line. This straight line we are having, it bends it into an S shape. Notice that the linear equation can output very big or very small values of z, but the output of the sigmoid function y prime is always gonna be between 0 and 1 exclusively. So that's something unique about logistic regression. Alrighty, our logistic regression model with 3 features has the following bias and weight. So we have b1. So suppose we have this and we are giving x1 0, x2 10, x3 2. So how do we calculate the z value in this case, right? So basically we know from our formula that y here, z here is b plus, so if we are doing b plus, that would be 1 plus 2 times 0, that is 0, minus 1 times 10, that is negative 10, 5 times 2 is 10. So negative 10 times, negative 10 plus 10 is 0. 2 times 0 is 0. B is 1. So basically, what this generates to for us, z is 1. Right? So if we want to check out, say what is the value of z for this input, so our z is 1. Exactly. So when we do 1 plus 2 times x1 and do all of that calculation, we get 1. Now the logistic regression model will now be a case of 1 divided by 1 plus exponential of negative 1. So how does that add to? So let's think about it. So 1 divided by, so we want to calculate exponential of negative 1. Since our z is 1, let me check what that gives us. Exponential. Let me just check if if I have an online calculator. Alright. So let's say we do an online calculator, and Let's do a scientific calculator. So we are doing 1 divided by 1. Let's go back. Sorry. 1 plus exponential of negative z, which is exponent 1 plus exponential. So we are doing negative 1. So the answer is 0.73. So this is our answer. Awesome. So we are done with that. So logistic regression, what is the loss? How do you calculate the loss? And how do you do the regularization? So logistic regression models are trained using the same process as linear regression models, with two distinctions. Logistic regression models use log loss as the loss function instead of a squared loss, and applying regularization is critical to prevent overfitting. We had discussed overfitting as when the data performs well, it so much learns the training data that it performs well with the training data. However, when you give it a new test data, it doesn't do as much. That is overfitting. All right. The following sections discuss these two considerations in more depth. So in the linear regression model, you use squared loss, also called L2 loss, as the loss function. All right. Squared loss works well for a linear model where the rate of change of the output value is constant. For example, given the linear model y prime equals to the bias plus 3 times x1, each time you increment the input variable x1 by 1, the output value y prime increases by 3. What that is saying is that if this is the weight, the bias, for example, but we have this weight standing by it, right? If we increase this value by 1, so let's say x1 is 1, this, whatever this will be, we increase by 3. For example, now it's 3 times 1. Let's make it x2 to be equal to 2. If x2 is equals to 2, then 3 times 2 is 6. It has increased by 3. However, the rate of change of a logistic regression model is not constant. As you saw in calculating a probability, the sigmoid curve is S-shaped rather than the linear. When the log odds z value is closer to 0, small increases in z result in much larger changes to y than when z is a positive value. It's a large positive or negative number. What this is saying is that if the input is 5, logistic output is 0.993. Input is 6 is 997. Input is 7 is 999. Input is 8 is 9997. When input is 10 is 99998, because it's having to work with this probability with the sigmoid curve. So this is, instead of the loss function for logistic regression, we use the log loss. All right. So the log loss equation returns the logarithm of the magnitude of the change rather than just the distance from data to prediction. Log loss is calculated as follows. So log loss, the summation negative y log y prime. This is a lot of math, but this is how we calculate log loss. Okay. And then, so what is regularization? It's a mechanism for penalizing model complexity during training. It's extremely important in logistic regression model. Without regularization, the asymptotic nature of logistic regression will keep driving towards zero in cases where the model has a large number of features. Consequently, most logistic regression models use one of the following two strategies to decrease model complexity: the L2 regularization or the early stopping, which is limiting the number of training steps to alt training while loss is decreasing. Alright, we're gonna test this now and see how well we do. So this is a test to test our knowledge on logistic regression. So why is a linear regression model's output a poor predictor of probability? Why is a linear regression model's output a poor predictor of probability? It only has one weight per feature. It only has one output value. The bias parameter skews the output. Its predictions are not restricted to values between 0 and 1. That's what I'll choose. So a sigma function never outputs the value 0 or the value 1. Yeah, it's going to give us values within the range, but not exactly 0s or 1. True or false, applied regularization is less important when training logistic regression models than it is. That is false. Which of the following options matches both linear regression and logistic regression with appropriate loss function for calculating loss? So definitely we know that the linear regression will use the mean squared error, while the logistic regression will use the log loss. Which of the following is an effective regularization technique for logistic regression model? That is early stopping, I think. So might get 4/5, I don't know, I think. Oh yeah, we got everything. So we passed. So early stopping is a regularization technique in which model training is stopped while loss values are still decreasing and can prevent overfitting. Alright, we got that. Awesome stuff. So we're gonna continue. So we are done with the brief introduction to logistic regression. The next thing we're gonna review is the classification model, where we go into a much more deep dive into the classification model. After that, this is part of the part 1 of our study series. When we finish this classification model, we will take a break, like a longer break, and come back again after an hour. So we'll take an hour break and then do another round. Let me just quickly check what we have here for the data. Okay, transformation, courses, data fitting. Alright, I think this is nice. So when we come back, we are going to go straight to advanced ML models, where we consider a review of the neural networks, embeddings, and large language models, and try to review that. That should be we'll round off this session probably in the next 30 minutes to 1 hour, then come back by maybe take an hour break, and then after the hour break we will do the advanced ML models to ensure that we have a comprehensive deep dive into all of these concepts. All right, I know we still have about 4 minutes in this session, so let's do that. We are done with 2 hours, so let's quickly review what we have to do here with classification model. So we started with the logistic regression part. We've talked about linear regression, we've talked about logistic regression. Now we are on classification. So the learning objective is to determine an appropriate threshold for binary classification model, calculate and choose appropriate metrics to evaluate a binary classification model, interpret ROC and AUC. So in the logistic regression module, you've learned how to use the sigmoid function to convert raw model output to the value of 0 and 1, but to make probabilistic predictions. For example, predicting that a given email has 75% chance of being spam. But what if your goal is not to output probability but a category? For example, predicting whether a given email is spam or not. Classification is a type of prediction, and predicting is the task of predicting which of a set of classes or categories an example belongs to. In this module, you will learn how to convert a logistic regression model that predicts a probability into a binary classification model. And that predicts one of two classes. We also learn how to choose and calculate appropriate metrics to evaluate the quality of a classification model's prediction. Finally, we'll get a brief intro into multi-class classification problems that are discussed in more depth later. Alright. So we are in thresholds and confusion matrix. So let's say you have a logistic regression model for spam email detection that predicts a value between 0 and 1, indicating the probability that a given email is spam. Okay? A prediction of 0.5 signifies that the email is spam. It's 50% likelihood that the email is spam. A prediction of 0.75 signifies a 75% likelihood that the email is spam, and so on. So you like to deploy this model in an email application to filter email into a separate mail folder. But to do so, you need to convert the model's raw numeric output 0.75 into one of two categories. Is it a spam or not spam? Okay? To make this conversion, you choose a threshold probability called a classification threshold. Alright? So we are almost at time. So it says examples of the probability above the threshold value are then assigned to the positive class. The class you're testing for here is spam. Example, the lower probability assigned to the negative class. The alternative class here, not spam. All right, so we then choose, okay, from which point. So for example, suppose the model scores one email as 99%, predicting that the email has 99% chance of being spam, and that email has 0.51, predicting it has 51% chance of being spam. If you set the classification threshold to 0.5, the model will classify both emails as spam. If you set the threshold to 0.95, only this email scoring 0.99 will be classified as spam. Why 0.5 might seem like an intuitive threshold, it's not a good idea if the cost of one type of wrong classification is greater than the other, or if the classes are imbalanced. For example, when we are dealing with cancerous cell, that is a very imbalanced scale that we need to be careful of how we choose our threshold. If only 0.01% of emails are spam, or if misfilling legitimate emails is worse than letting spam into the email box, labeling anything the model considers at least 50% likely to be spam as spam produces undesirable result. What this is saying is that it depends on what is the cost of a mistake. Hence, the confusion matrix. The confusion matrix, I know we discussed that yesterday in this when we reviewed our stuff, our refresher course. The probability score is not reality or ground truth. There are 4 possible outcomes for each output from a binary classifier. For the spam classifier example, if you lay out the ground truth as columns and the model's predictions as rows, this is columns, the actual negative, actual positive, predicted positive, and predicted negative. So we have a confusion matrix. So a true positive, a spam email correctly classified as a spam email. That's a true positive. These are the spam messages automatically sent to the spam folder. A false positive is a not spam email misclassified as spam. Say for example, a recruiter tries to reach out to you, send you a job opportunity, and then it gets sent to your spam folder. That is a false positive. These are the legitimate emails that wind up in the spam folder. A false negative is a spam email misclassified as not spam. These are spam emails that aren't caught by the spam filter and make their way into the inbox. Remember, this column is for the actual positive. Now, it was predicted as negative. That is why it's a spam email, but we misclassified it as not spam. While the true negative is a not spam email correctly classified as not spam. These are emails that are sent directly. These are the legitimate emails that are sent directly to the inbox. So they are a not spam email correctly classified as not spam. These are so the truth in the case of a spam, this is the one you want to get. They are not spam emails and they are correctly classified as not spam and they are sent to our emails. Notice that the total in each row give all the predicted positive. So when we look at this, the true positive plus false positive, that's the positive predicted positive. And then the predicted negative are the false negative plus the true negative. And if we want to calculate accuracy, we say the true positive plus the true negative divided by the total. In that case, those that are truly spam that are classified as spam, those that are not spam that were classified as not spam, divided by the total emails you're receiving. When the total of actual positive is not close to the actual negative, the total of actual negative, the data is imbalanced. An instance of an imbalanced data set might be thousands of photos of clouds where the rare cloud type you're interested in, say volutus cloud, only appears a few times. Or in cases where you're having like bank transactions, most of your transactions will be legitimate, and the transactions that are fraudulent will actually be more smaller compared to all the transactions you are having. If you're having a balanced scale of true transactions and false transaction, I would say just close that bank account. Alrighty, we'll take a 5 minutes break here, come back to review these three concepts, and then we'll take a 1 hour long break. All right. Alrighty. So we'll take a 5 minutes break and we'll be back. All right, we'll be getting started um with the next session now. All right, so we go on to review. I know we discussed this yesterday. Accuracy, precision, and recall, and related metrics. So true and false positives and negatives are used to calculate several different metrics for evaluating for evaluating models. Which evaluation metrics are most meaningful depends on the specific model and the specific task, the cost of different misclassification, and whether the data set is balanced or imbalanced. All of these metrics in this section are calculated at a single fixed threshold and change when the threshold changes. Very often, the user tunes the threshold to optimize one of these metrics. So accuracy, this is the proportion of all the classification that were correct. Just like we're saying, if in a case whereby we have true spam filters, if we have a spam detection machine learning algorithm and it truly classified it as a spam, and the ones that it truly classified the ones that are spam as spam and the ones that are not spam as not spam, the addition of that divided by the total data we are dealing with, the total classification, is the accuracy. Just like I said, so it means the fraction of all the emails correctly classified. A perfect model, we have 0 false positive and 0 false negative, and therefore an accuracy of 1, which is a very rare case because it incorporates all 4 outcomes from the confusion matrix, giving a balanced data set with similar numbers of examples in both classes. Accuracy can serve as a coarse-grained measure of model quality. For this reason, it is often the default evaluation metric used for generic or unspecified models carrying out generic or unspecified tasks. However, when the dataset is imbalanced or when one kind of mistake, the false negative or false positive, is more costly than the other, which is the case in most real-world application, it's better to optimize for one of the other metrics instead. For heavily imbalanced data sets where one class appears very rarely, say 1% of the time, like a rare cell in babies or something like that, or a rare disease in pregnant women, a model that predicts negative 100% of the time would score 99% on accuracy despite being useless. That's something we should note. Note, in machine learning, words like recall, precision, and accuracy have mathematical definitions that may differ from or be more specific than more commonly used meanings of this word. So this is machine learning terminology for accuracy. It doesn't necessarily talk about the general linguistic meaning of this term. So recall or true positive rate. So the true positive rate or the proportion of all actual positive. So the recall talks about the true positive rate. So it's talking about all the true positive all actual positives, so that were classified correctly as positive. That's the recall. So for example, the correctly classified actual positive, that's the true positive, divide by all actual positive. All actual positive means that those that are truly actually positive, like the true positive itself, and the false negative, meaning that even though the model predicted it to be wrong, in the real sense it was actually the right thing, right? So it's a false negative. Okay, false negatives are actual positives that were misclassified as negatives, which is why they appear in the denominator. So denominator means the lower part, the nominator, I think nominator is the top part, denominator is the down part, or something like that. In the spam classification example, recall measures the fraction of spam emails that were correctly classified as spam. This is why another name for recall is probability of detection. It answers the question, what fraction of spam emails are detected by this model? So probability of detection. A hypothetical perfect example would have 0 false negative and have a recall the total positive rate or true positive rate of 1.0, which is 100% detection rate. In an imbalanced data set where the number of actual positive is very, very low, say 1 to 2 in total, recall is less meaningful and less useful as a metric. The false positive rate is the proportion of all actual negatives that were classified incorrectly as positive. This is the probability of false alarm. Probability of false alarm. So incorrectly classified actual negative. So the false positive divided by the false positive plus true negative. So false positives are actual negatives that were misclassified, which is why they appear in the denominator. In the spam classification example, false positive rate measures the fraction of emails that were incorrectly classified as spam. That's the false positive rate. Now, precision is the proportion of all the model's positive classification that were actually positive. So this is the mathematical definition for precision. So correctly classified actual positive over everything classified as positive. In the spam classification example, precision measures the fraction of emails classified as spam that were actually spam. So for example, if the model predicted that we had say 75% spam, right? However, as total, it predicted we are 75% either as false positive or true positive, and then the true positive that is like maybe 25%, so that would be 25 over 75 or 30 over 75 depending. So correctly classified actual positive divided by everything classified as positive. So choice of metrics and trade-offs, right? Accuracy. Use a rough indicator. Use as a rough indicator of model training progress or convergence for balanced data set. For model performance, used only in combination with other metrics. Avoid accuracy for imbalanced data set. Recall used when false negatives are more expensive than false positive. False positive rates used when false positive are more expensive than false negative, and the precision we use it when it's more important for positive predictions to be accurate. This is F1 score. We discussed this yesterday. This is 2 times precision times recall over precision plus recall. So basically, if we have something like this, we just put it. So this is 2. The F1's, it says calculate the recall. Calculate the recall. We recall that the recall is the true positive rate and the true positive rate will be the true positive divided by the true positive plus the false negative. So the true positive plus false negative. So true positive is 5. So we are doing 5 divided by true positive 5 plus the false negative 2. So this is 5 divided by 7. So we come and say, let's go back and say 5 divided by 7. So 0.714. That's our answer right there. Yeah. And then what is the precision? The precision is the true positive over all the positives, right? So the true positive over all the positives, that's the precision. So we are doing the true positive 3 divided by all the positive, which is 3 plus 2. So that is 3 divided by 5. So we say 3 divided by 5, 0.6. Yep. So you are building a binary classifier that checks photos of insect traps for whether a dangerous invasive species is present. If the model detects the species, the entomologist, insect scientist on duty is notified. Early detection of this insect is critical to preventing an infestation. A false alarm is easy to handle, so that's not a real issue. The entomologist sees that the photo was misclassified and marks it as such, assuming an acceptable accuracy level. Which metric should this be optimized for? So they said a false alarm. So since we need an early detection of this model to prevent an infestation, when we go back, we see that in that case, false positive are more, a false negative is more expensive than false positive. So a false positive is more expensive than false negative. So it's either going to be a recall or a false positive rate. So let's read again. We are checking for dangerous invasive species if it's present. If the model detects the species, the entomologist on duty is notified, and early detection of this insect is critical to prevent an infestation. Okay, a false alarm is then easy to handle. In that case, I would say that it's better to think of it like, since I will go with it, this instead of recall. I will check. Is it that one of them? But I'll go with false positive rate. I might be wrong. Okay, said false alarm are low cost. So this statement here that a false alarm is easy to handle makes the answer recall. Yeah, since false alarm are low cost, false negatives are highly costly. So it makes sense to maximize recall. That makes sense. So basically, since from the example we're given, a false alarm is easy to handle, so that means that it's not the most expensive, it's more so recall, because we use this when the false negative is more expensive than the false positive. The false negative, if we don't detect it early, it can lead to infestation. So that's why recall is the answer. So I missed it when I first thought of this being a high cost, but it's a low cost. All right, so we did this yesterday where we talked about the ROC and the AUC curve. The previous section presented a set of model classification, all calculated as at a single classification threshold. But if you want to evaluate a model's quality across all possible thresholds, you need different tools. So we can use the ROC curve, receiver operating characteristics curve, is a visual representation of a model performance across all thresholds. The long version of the name receiver operating cost is a holdover from World War II radar detection. Okay, learning new things. So the ROC curve is drawn by calculating the true positive rate and the false positive rate at every possible threshold. Alright, so this is the area under the curve. So the ROC curve is drawn by calculating the true positive rate and the false positive rate at every point, at every possible threshold. In practice, at selected intervals, then graphing TPR over FPR, the true positive rate over false positive rate. Alright. The area under the curve, area under the ROC curve, represent the probability that the model, if given a randomly chosen positive and negative example, will rank the positive higher than the negative. So for example, in a spam detection classifier, a spam classifier with AUC of 0.5 assigns a random spam email a higher probability of being spammed than a random legitimate email only half the time. Alrighty. So AUC and ROC for choosing model and threshold. AUC, area under the curve, is a useful measure for comparing the performance of two different models as long as the data set is roughly balanced. Okay? If it's an imbalanced data set, we can use precision recall curve. Let's see what that looks like. So this is the precision recall curve. So AUC and ROC work well for comparing models when the data set is roughly balanced. When the data set is imbalanced, we use a precision recall curve, and the area under those curves may offer a better comparative visualization of model performance. Okay? Precision recall curves are created by plotting precision on the y-axis and recall on the x-axis. So precision on the y-axis, recall on the x-axis. So the model with greater area under the curve is generally the better one. So this is actually better than this. The points on a ROC curve closest to 0.1 represent the range of best performing threshold for the given model. So this is A is better. If false positive are highly costly, it will make sense to choose a threshold that have a lower false positive rate, like the one on point A, even if TPR is reduced. Conversely, if false positive are cheap and false negatives miss true positive is highly costly, then C will be better. If the costs are equally relevant, equivalent, then we choose B. So in practice, ROC curves are much less regular than the illustration given above. Which of the following models represented by the ROC and AUC has the best performance? I'll say this. The one with the highest. Which of these performs worse? Yeah. Let's see. Which of these changes can be made to the worse than chance in the previous question to perform better? So the question was for it to predict so I would test. I say okay, so that's wrong. If a binary classifier reliable puts examples in the wrong classes, more often than not, switching the class labels immediately makes the prediction better without having to retrain the model. Interesting. Imagine the situation where it's better to allow some spam to reach the inbox than to send a business critical email to the spam folder. You've trained the spam classifier for this situation where the true positive class is spam and the negative class is not spam. Which of these points on the ROC curve? So basically they are asking which one is more costly. And when we go back here, we saw that when we are choosing a point, if the false positive are more costly, we choose a threshold with a lower FPR. Alright. So if false positive are cheap and false negatives is highly costly, that is missed true positive, which is our case, we choose C. Wait, maximizes true positive. This threshold maximizes true positive. Flags more spam at a cost of a more false positive. Go back, let me go back. It says that if false positives are highly costly, it may make sense to choose a threshold that has a lower alright. So that would be so want to minimize false positive. That makes sense. I missed the understanding there. Alright, prediction bias. As mentioned on the linear regression models, calculating prediction bias is a quick check that can flag issues with the model or training data early on. Prediction bias is the difference between the mean of a model's prediction and the mean of the ground truth label. Okay, a model trained on a data set where 5% of the emails are spam should predict on average that 5% of the email it classifies as spam. In other words, the mean of the labels in the ground truth dataset is 0.05 and the mean of the model's prediction should also be 0.05. So what causes biases or noise in the data, including bias sampling of the training set, 2, strong regularization, meaning that the model was oversimplified and lost some necessary complexity, bugs in the model training pipeline. Alrighty, time is gone. Alright, we'll resolve this in neural networks. Multi-class classification can be treated as an extension of binary classification to more than 2 classes. Alrighty. Then I think there's a programming exercise where we test it out. Let me see. So this is Google Colab. And we'll explore the data set. Alright, so this is where we can test this out. I will have another one where I do like just the programming exercise and test it out. But for now, I'm just refreshing the knowledge. Let's do the quiz and be done. Increasing a binary classifier's threshold value is likely to produce which of the following effects? If we increase the threshold, so basically suppose for the spam detection, we're supposed to have it, say it's on 0.5, but then we raise it up to like 0.9. That's the meaning of increasing the threshold. What happens? We have a situation where the false positive. So what is false positive? I have to recall that. So let's go back because this is important. So the false positive, a not spam email misclassified as spam. That's not what happens. So if we increase it, a not spam email, what happens is that a spam email is actually misclassified. A spam, so a not spam email misclassified as spam, that's what happens. So that increases. That's my guess on that. The data set that you split, because it increases because you have increased the stuff now. The data set that you split into train, test, and evaluate sets has 9,998 negative examples and 2 positive values. The resulting model has an accuracy of 99%. Can you trust this model based on accuracy? Nope. In general, when precision increases, what happens to recall? When precision increases, let's go back. So what is precision? And let's think about it. So precision is calculating the true positive that were gotten from all the classification of all the positive. Then recall is the true positive from all actual positive. So when precision increases, I would say that recall should also increase though, because what is the relationship between precision and recall? Let's think about it. What is the relationship? So these are the correctly classified. So in spam, precision measures the fraction of emails classified as spam that were actually spam. So precision improves a false positive. Precision improves as false positive decreases, while recall improves as false negative decreases. So there's an inverse relationship. But as seen in the previous section, increasing the classification threshold tends to decrease the number of false positive and increase the number of false negative, while decreasing the threshold as the increasing the classification threshold tends to decrease the number of false positive. It tends to decrease what? But as in increasing the classification threshold tends to decrease the number of false positive and increase the number of false negative. So it decreases false positive. Decrease false positive. Then here there's an inverse. So when precision increases, recall decreases. The points on binary classification's ROC curve closest to 1, generally represent the best performing threshold for the model. I'll say true. Let's see that. Yeah. Bless me. Says a perfect model. Alright. A perfect model with that which has some threshold as alright. You are evaluating the performance of two binary classification models. Model A and Model B have an AUC of 0. Model A has an AUC of 0.5. Model B's predictions are made completely randomly. I don't know how you can do that. Let's check it. A model that does exactly as well as a random flip, as a random guesses or coin flip, as I already said, that is diagonally 0 to 1, right? The AUC 0.5 represents 50% probability. So in the spam diffuser, a spam diffuser with 0.5 assumption, a spam classifier with AUC of 0.5 assigns a random sample email a higher probability of being spam than random legitimate email only half the time. So I think they would both do equally. I say they do equally. I might miss some. So I got there. Okay. That makes sense. So I got 80%. I needed to learn there. So which one did we miss? Here. That is false. Alrighty. So we come to the end of these sessions of study. We've done a review on ML models where we went through linear regression, logistic regression, binary classification. In the next, we'll be going to advanced ML models to review this, neural network, embeddings, and large language model, and see where we can reach with that. Alrighty. Alrighty. We'll bring it to an end right now. We've been here for about 3 hours, completing this study session where we reviewed machine learning concepts. Very interesting stuff. So we'll probably still have another session around from 7 p.m. To review some deep learning stuff. Yeah. We'll see how that goes if I'm able to come online. If not, yeah. But thank you so much for tuning in and staying with me through these 3